Hello, and welcome to the mean value theorem. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is Applications of Differentiation, Chapter 3 of the Larson's Calculus text. It's for Math 1411 at UTEP, Calculus. Section 3.2 is Rolle's theorem and the mean value theorem. And this is part 2 of the two-part lectures. The first part was on Rolle's theorem, and now I'm going to talk about the mean value theorem. So the mean value theorem. If f is continuous on the closed interval from a to b, so our function is continuous on the closed interval from a to b, and is differentiable on the open interval, so the derivative exists everywhere except possibly at the endpoints, then there exists a number c in the interval from a to b, in the open interval, such that the slope of the line at C is equal to the slope of the line connecting the endpoints, right? That's all f of b minus f of a over b minus a is. That's a fancy way of saying y2 minus y1 over x2 minus x1. This is just the slope formula. I have 2 points. I can find the slope of the line between them. The mean value theorem says if f is continuous on a closed interval and differentiable on an open interval, then the slope of the line connecting the endpoints will be matched for some point in that interval. So blue line connecting the endpoints, if I slide my tangent lines along the graph, here's a value of c, where the slope of the tangent line is the same. And I'd hazard a guess there's one here as well. But the mean value theorem says there is at least one. So let's determine whether the mean value theorem can be applied to f on the closed interval. If so, we're going to find the value of c. If not, let's see why not. Number 1, f of x equals x cubed on the interval from 0 to 1. X cubed, polynomial, it's continuous and differentiable everywhere, so we know the mean value theorem applies. I'm going to evaluate the endpoints. F of 0, 0 cubed is 0, and f of 1, well, 1 cubed is 1, so I have the values of my endpoints and I can find my derivative. The derivative of x cubed is 3x squared. So what does the mean value theorem say? It says that f prime of c, which in this case is 3c squared, is equal to the slope of the line through the endpoints. Well, what's the slope of the line through the endpoints? That's 1 minus 0. At the outputs, 1 minus 0, divided by the inputs, 1 minus 0. I want to solve 3c squared equals 1 minus 0 over 1 minus 0. That's a pretty odd way of saying 3c squared equals 1. Let's divide both sides by 3. And then we'll take the square root. But remember, anytime you take the square root of a value, you have to include the plus or minus. So c equals plus or minus the square root of 1/3. After simplifying, and I'm going to write this down because let's just look at the positive square root. The square root of 1/3, using the quotient rule, is the square root of 1 over the square root of 3. Let's make that a 3. We all know the square root of 1 is 1. The square root of 3, maybe you don't know that one. But to rationalize, we're going to multiply both numerator and denominator by the same value. Mathematician's trick. Multiply by a form of 1, and 1 will look different depending on what you need. I know that 1 times the square root of 3 is going to give me a square root of 3 in the numerator. Pretend that's a 3 with me. I can't pretend that well, I'm sorry. There we go. And the square root of 3 times the square root of 3 is 3. This is where I get this answer. But I only used the positive square root of 3 over 3. I did not include the negative square root of 3 over 3, and that goes back to my interval. I have to pay attention to what I want for my answers. The c value has to be between 0 and 1. Therefore, the negative doesn't come into play here. Number 2, f of x equals x to the 4th minus 8x on the interval from 0 to 2. Yet again, a polynomial, continuous and differentiable everywhere. F of 0 is 0. F of 2, 2 to the 4th is 16. 8 times 2 is also 16, so I'll have 16 minus 16. Notice that since the values of the endpoints are the same, Rolle's theorem also applies because Rolle's theorem is a special case of the mean value theorem. Our derivative is 4x cubed minus 8, and the mean value theorem says that f prime of c, 4c cubed minus 8, is equal to 0 minus 0 over 2 minus 0, the slope of the line connecting the endpoints. And of course 0 minus 0, my numerator, gives me a 0 for my output. 4c cubed minus 8 equals 0. I'm going to add 8 to both sides. I'm going to divide by 2, so I end up with a c cubed equals 2. Let's say that correctly. I'm going to add 8 to both sides and then divide by 4 in order to get 2. I think I said that wrong the first time. If c cubed equals 2, then c is the cube root of 2. The cube root of 2 is positive, and it is less than 2, so I know that it's in the appropriate interval, 0 to 2. This is a fantastic answer. If your homework asks you to round to 3 decimal places, that's when you reach for the calculator. But if it does not tell you how to round, use the exact value and don't round. F of x equals x plus 1 over x. I know that this function has a domain issue at x equals 0. 0 is in our interval, so this is not continuous nor differentiable at x equals 0. Mean value theorem doesn't apply. And yes, you will have 1 or 2 of those on the homework, but I wouldn't expect it on an exam. Number 4, f of x equals sine of x on the interval from 0 to pi. Sine of x is continuous and differentiable everywhere. It's a nice function. F of 0 is 0. F of pi is 0. So again, Rolle's theorem also applies. The derivative of sine is cosine. So I can solve for c. The cosine of c equals 0 minus 0 over pi minus 0. Cosine of c equals 0. Well, if cosine is 0, then I know that c has to be pi over 2, because where is c 0? C is 0 at pi over 2, 3 pi over 2, 5 pi over 2, all odd values of pi over 2. And for this particular interval, 1 pi over 2 is the only option. Rolle's theorem, special case of the mean value theorem, which the endpoints are equal. Alright, so a plane begins its takeoff at 2 p.m. on a 2,500 mile flight. After 5.5 hours, the plane arrives at its destination. Can you believe I still have typos in here? No matter how many times I read it. The plane arrives at its destination. Explain why there are at least 2 times during the flight when the speed of the plane is 400 miles per hour. Well, on average, the plane flew at 2,500 over 5.5, 2,500 miles over 5.5 hours, or 454.5 miles per hour. In order to average this speed, it had to go from 0 up to full speed, which is somewhere past 454.5 miles per hour, and then it had to power back down to land. Right? What is this? This is the slope. This is the average of the endpoints from 0 to 2,500 miles later, 0 to 2,500 miles later, and time 0 to 5.5 hours. So this is the average. This is the f of b minus f of a over b minus a. And we know that it had to go at least 400 miles per hour in order to hit its average, and it had to pass back through 400 miles an hour to land. So mean value theorem, in this case Rolle's theorem, works out for us. It's all good, and it works in real life too. That's it for section 3.2, Rolle's theorem and the mean value theorem. If you didn't listen to part 1 of the lecture, you might want to go back and check that out. Thanks for listening.